Hello everyone. In this video, we are going to study about the different modes of failure of the beams. So let's start. So whenever we study about the beams, whether it is in RCC structures or in the steel structures, the primary modes of the failure of the beams are because the beam transfers the load with the help of the bending moment and the shear force. So these are the two primary modes of failure, that is the bending failure and the shear failure. And in addition to that, if the beam is subjected to the deflection given the end condition, then the another type of failure will be the deflection failure. So we need to study about the beams with these failures. So the bending failure, it generally occurs whenever there is a crushing of the compression flange or the fracture of the tension flange of the beam. So as we have studied that if we distribute the stress throughout the beam section, so this is the shape that we get for the stress distribution diagram, in which the top flange is in compression while the bottom portion is in tension. So the top portion will be subjected to the compressive forces. That's why there will be the crushing of the compression flange, while the bottom portion is subjected to the tensile forces, because of which there will be the fracture of the tension flange. And this failure is known as the bending failure. Next type of failure which may occur in any beam, that is the shear failure, which is generally because of the buckling of the web of the beam near the location of the high shear forces. And these high shear forces are generally around the support section of the beam. So the beam can fail locally due to the crushing or buckling of the web near the reaction of the concentrated roots. And these reactions are primarily acting at the support. So that's why the position of the shear failure is at the position near the support. So usually they fail up along the support section. Now the third type of failure which occurs in the beam section, that is the deflection failure. So always a beam is designed to have adequate strength, but it may be possible that the at some point of time the load which is acting on the beam, it is exceeding that limit, and in that time it is not suitable to carry the amount of load which it can. So that means if the load capacity is exceeded, then it may not be possible for the beam material to support the load without excessive deflection. And the deflection will be shown here. Although this deflection or deformation which is shown here, it may not be causing the failure of the beam structure, but it would not be pleasing to the aesthetic point of view, and that's why it will be failing in the serviceability criteria. And because of that, the structure need to be revised. That means it has to be redesigned so as to achieve the suitable deflection criteria. Now, other than this, the two type of failure also occur in case of the steel beams, and they are because of the buckling. Now, this buckling may be because of the general loading condition, that the deflected shape is in this form, that let's say this is an I section, and if this I section is deflected in this form and it is shifted laterally, let's say this is the now the I section shape. So if this shape is obtained in such a way that there is some lateral distribution, lateral deformation of the beam, then that type of failure is known as the lateral buckling. While if there is some torsion along with the lateral buckling, then that type of buckling is known as the lateral torsional buckling. So this lateral buckling, it may be again for the complete system or for a part, which is known as the local buckling. So it has been shown here. So if the complete system fails, so it is known as a distorted web. While if some component of the web portion is crippling or deflecting, then that type of failure will be known as the local buckling. Now, for the hot rolled beams, that means the rolled beams that we are usually providing for the beam section. So for them, we are having four categories of the failure criteria. So in the category 1 of the failure criteria, it says that whenever the beam is failing under the excessive bending, it may be collapsing. So that is the first criteria, and it is when the beam is prevented from buckling laterally. That means whenever the beam is subjected to the heavy loads, and because of that the bending moment is very heavy. But in any condition, the beam is not allowed to move laterally in the horizontal direction. Let's say this is the beam cross section, so it is not allowed to move in these directions. So whenever it is restricted from the lateral movement, it will be subjected to the heavy bending moment. And the component elements are at least compact. That means we are having different capacity of the sections. So slender plastic movement and the compact section and semi-compact sections. So the compact section, they do not buckle locally. That means they must be strong enough. And this type of beams are usually the stocky beams. That means these are the heavy beams which do not buckle locally. Therefore, in this condition, the only failure criteria will be because of the plastic hinge formation. As we have studied that the stress distribution diagram for the normal beam, that is shown by this diagram. So at the top it is compressive forces, while at the bottom it is tensile forces, and at both the position the extreme fibers reach up to the yield stresses. So when we increase the load further, so what happens, the nearby members, they reach the yield stress, while the rest of the members are still under the lesser values of the yield stresses. But at the point of time when the complete section is under the yield stress, now at this point of time, what will happen? Let's say if this was a simply supported beam, then all the points of support and at the position of the load, these will be developing the plastic hinges. These will be developing the plastic hinges, because of which the complete section will be showing the deflection, and this is the collapse condition of the plastic hinge. So this is the first category of the hot rolled beams in which we classify the different failure modes. So it is the excessive bending triggering the collapse. Now in the second category, the lateral torsional buckling occurs. So it is predominant in case of the longer beams. So this is the important criteria, that whenever we are having the longer beams, such as the span of the bridge or of the deck of any flyover that we see, so in those cases there are very high chances of the lateral torsional buckling. Now these are, if not suitably braced, that means if they are not restricted in the vertical direction or in the horizontal direction, the bracings are provided along the length or the depth. So if they are not braced properly in the lateral direction, that is unrestrained beams, there is no restraining of the beams, then that type of failure falls under the category 2 of the failure modes of the hot rolled beams. So as you can see here, if this was the beam, let's say I'm drawing it again here, so let's say this is the I section which was at this position. This was the I section which was at this position. Because of the excessive load, what will happen, this will be transferring in the lateral direction, as well as there will be some movement because of the eccentricity present. Now this failure occurs by a combination of the lateral deflection as well as the twist. So laterally the beam will be deflecting and there will be some twisting movement because the load is not applied along the plane of symmetry. And the proportions of the beam, support condition, and the way the load is applied are all the factors which affect the failure by lateral torsional buckling. Because for different end conditions, there will be different amount of bending moment which will be generated, and because of that, the buckling will be occurring. Now, this is the example of the actual images or actual lateral torsional buckling. So you can see that this beam is being shifted in the lateral direction, as well as there is some movement in the beam. So this type of failure is known as the lateral torsional buckling, which falls under the category 2 of the failure of the hot rolled beams. Now the third type of failure for the hot rolled beams is because of the local buckling of a flange or a web. Now this flange will be failing because of the compression, while the web may fail because of the shear or because of the compression both. And these shear and compression, when they are because of the concentrated load, that falls under the category 3 of the failure modes. Now what happens, so whenever we are using the hot rolled steel sections, they are stocky in nature, that means they are heavy. they are capable enough to carry the heavy loads, if not the capacity. But when we are designing the fabricated box section, so what happens? So let's say this is the channel section and this is another channel section. So these channel sections are used or joined together at these points to obtain the box section. So this is the box section. Now this box section may require the flange stiffening to prevent the premature collapse. So now what will happen? So whenever we are providing this box section along the length, so let's say this is the length of the box section. Now because of the excessive compressive load along the flange section, there will be some deformation, a wave-like formation on the top section. As you can see here, that because of the compressive load, this flange section have shown the premature collapse because of the excessive compression. Now the whole system is not collapsing, only the component of this section is collapsing, and since only one component is showing the collapse condition, that's why this is known as the local buckling failure, which is under the third category of the failure. Now next type of failure will be in the local buckling when the web is subjected to the shear. The shear is predominant at the support conditions or near the supports. So at those conditions, what will happen? Because of this shear, there will be a diagonal compression which will be there, and because of the diagonal compression also there will be wave like formation. Again, this will be the local buckling because only the component of the web is buckling. So at this position we need to stiffen the web so as to avoid this compressive forces distortion. So web stiffening may be required for the plate girders. So plate girders are usually used for the built-up sections. That's why their name comes as the plate girders. To prevent the shear buckling, we will be requiring the web stiffeners. So we will be providing stiffeners here so as to avoid the diagonal compression. Now there is another chance that the load may be in such a way. Let's say this is the steel section. Let's say this is the steel section at which the concentrated load is acting. Now when this concentrated load is acting, and if this load is very heavy, so it is possible that the beam section is not possible to distribute this uniformly, and because of which the web buckling may occur because of the heavy loads acting at the point of concentration. So to avoid these type of conditions, what we do, so whenever we are having the I section, usually we prefer the I section for the design that we have seen in the previous video. So if there is the concentrated load which is acting, so as to avoid the local buckling of the web, what we do, we need to distribute the load uniformly. So for that we need to increase the area because we know that this load is equal to stress into area, or stress can be written as load upon area. So if we increase the area of the distribution, the obviously the stress which will be coming into this section will be decreasing. So to use this principle, what we do, we provide the bearing plates at the top of the section, and now the distribution of the load will be in this manner. So it has been distributed up to a larger area, because of which the stress is decreasing on the steel section, and that's why we prevent the web buckling. So to resist the web buckling, load bearing stiffeners. So these load bearing plates are provided at the top portion and under the point load so as to resist the web buckling. Now the fourth criteria of the failure is the local failure by shear yield of the web. That means the web may be yielding under the shear, or the local crushing of the web because of the constant heavy load, or the buckling of the thin flanges. If we are providing the thin flanges, then all these type of failure falls under the category of the fourth number of failure modes of the hot failure modes of the hot rolled steel sections. So the shear yield, this can only occur in very short spans. So in very long spans, the lateral torsional buckling occurs, and in very short span, the shear yielding occurs. And whenever the shear yielding is occurring, therefore we need to strengthen the web by providing suitable stiffeners. So the suitable web stiffeners have to be redesigned for the member. So that means we will be providing the stiffener along these sections so as to carry this heavy load suitably. Now the next possible failure is local crushing. So local crushing is possible when the concentrated load act on an unstiffened thin web. So this is the example of the unstiffened thin web. So this is the thin web which is provided here. Now if the heavy concentrated load is acting here, which may be acting here, so at those positions what is happening, the local crushing of the failure is occurring. That means this only this portion of the web which is the at the root of the fillet, that means at the root of the junction of this flange and the web, this section is experiencing the heavy load, because suddenly at the flange section the load was transferred through this area and suddenly this section has reduced by this much amount and this is remaining this much. So let's say that initially the flange width was 100 millimeter and the web width is 20 millimeter. So that means there is an 80% decrease in the thickness of the portion which is transferring the load. So because of that, suddenly the large stresses come onto the section, because of which there are chances of the crushing of the web. So to avoid that, what we do, we need to provide the suitable web stiffness. Then if the flange section that we are providing, if that is very thin, then there are chances that the buckling of the thin flanges may occur because of the high compressive stresses. If there are compressive stresses along these axes, then in that condition it may be possible that the flanges may be buckling. So for that what we do, we either provide the short flanges, and this problem is predominant when the wide flanges, because of wide flanges what will be happening, if this is the wide flange, so it will be having certain width and it will be having certain thickness. So this BF by TF ratio, that is the width to thickness ratio, if this is increasing then there are chances of the buckling. But if we increase the thickness or we decrease the width, in those conditions the chances of the buckling will be decreased. So that's why these are predominant whenever the wide flanges are employed. And for that what we do, we weld the additional flange plate which will reduce the plate width to thickness ratio. Because if we provide the additional plate, for example if we provide the plate on top of it, so now the thickness will be increasing, and now let's say thickness is increased by this much amount. Now let's say this is the T dash value. So B by T dash, so this B by T dash, because the thickness is increasing, so this ratio will be decreasing. And since this ratio is decreasing, so the chances of the flange buckling can be avoided. So these are the four type of failure for the hot rolled steel sections. Now for the torsional buckling criteria, the code says different conditions, and for that code has given the different values for the length of member which can be taken so as to avoid torsional buckling with the help of the suitable stiffness factors. Now the deflection formula for the torsional little buckling. Now in general, the maximum deflection criteria that has been laid out by the codal provision of IS 800 2007 edition, it is given by delta dash is equal to K times WL cube upon EI, where K is a constant which is dependent upon the load distribution and the support condition. W is the load which is acting on the beam, L is the effective length of the span, and this EI is the Young's modulus and the moment of inertia of the steel section respectively, and this delta dash is the maximum deflection which will be occurring under this load on the span. So this is the value. We will not be using this because for different type of conditions there are different conditions, but in general if nothing is given then we will be using this formula for finding out the maximum deflection and to check whether the beam is under the limits or not, and if not then we will be providing suitable stiffness. Now in the next video we will be looking at the two types of the local buckling failures, that is the web crippling and the web buckling. So thank you.